Hello, this is John Wallace, Senior Editor at Laser Focus World, and welcome to today's webcast brought to you by Laser Focus World Online. Today's event, Virtual Simulation for Pulse Oximetry Wearables, will be presented by Michael Govan, Vice President of Sales and Marketing at Lambda Research Corporation. Before we begin, I'd like to first cover a few housekeeping items. At the bottom of your audience console are multiple application widgets you can use. If you have any questions during the webcast, you can click the Q&A box and submit your question. We will try to answer these questions during the Q&A session after the webcast, but if a fuller answer is needed or we run out of time, they will be answered later via email. We do capture all questions. Also, if you have any technical difficulty, please click the Q&A box and our tech team will assist you. You can expand your slide area by clicking on the Maximize icon on the top right of the slide area or by dragging the bottom right corner of the slide area. A PDF copy of today's presentation is available using the Resource List widget that looks like a green folder at the bottom of your screen. For your convenience, this presentation will be available on demand within 24 hours of this live event. A reminder email message will be sent to all registrants with a link to the archive. It will be accessible from the home page at www.laserfocusworld.com. Now it gives me great pleasure to introduce today's speaker, Michael Govan.
Hello, everyone, and thank you for attending the virtual simulation for Pulse Oximetry Wearables webinar. I'm going to flip you over to our slide and introduce you to a little bit about Lambda Research. Lambda Research has been in business for over 20 years, and we set ourselves apart by offering cost-effective, single-source, optical, optomechanical, and illumination design software solutions. We have two major products for the illumination design and analysis portion, and that is TracePro, our flagship program, which is a CAD kernel capable of doing virtual prototyping, which is accurate, easy to use, very intuitive. The interface is a completely graphical user interface based on the standard CAD engine and has a very, very short learning curve. We are the quickest return on investment in terms of illumination design software, especially in the biomedical field. Our RayViz product is a SolidWorks add-in, and what's really unusual about our RayViz product is that there's only three icons, three menus to learn how to use the product. Pretty much what you do is you get the TracePro system tree inside of SolidWorks, where you can apply optical properties, you can ray trace directly in SolidWorks, and then you can export a native file directly to TracePro, ready for ray tracing. Our agenda today is that medical engineers and scientists have a lot of challenges when designing devices for pulse oximetry. In this webinar, we're going to investigate both a transmissive and a reflective design and see how we can incorporate the newest technology into those designs and then get rid of stray light and other types of problems. We'll first look at general background to understand the optical principles in pulse oximetry designs. And then we're going to go through a couple of examples where we investigate throughput, crosstalk, stray light issues. And we're going to use TracePro to do that virtual prototyping. As everyone knows, virtual prototyping is now the industry standard for doing this type of analysis and pulse oximetry devices. It really helps to expedite the design phase. With this full demonstration of these two examples in both the transmissive and reflective systems and using TracePro, we're going to go through and see where problems are, where they exist, and how to get rid of them. Let's go into a little bit of background on pulse oximetry. Pulse oximetry has been around in use since the 1970s and has been widely adopted by hospitals to do oxygen saturation, pulse rate monitoring of patients by applying a device to their fingertip, forehead, foot, or earlobe. The application for these devices has remained pretty much stagnant for 40 years. But in the past few years, there's been a very large growing interest in wearables for track, health, fitness. And that's where we've taken pulse oximetry out of the hospital and into the general consumer market. So that now that we're looking at a much larger market, there's been a lot of interest of how we can do this as a wearable on the wrist or somewhere else on the body, not necessarily in the hospital where someone's staying stagnant laying in a hospital bed, but these people are running around expecting to be able to have a instantaneous oxygen rate given to them. So this makes things difficult, and medical device engineers and scientists are now developing innovative pulse oximetry devices that have unique design challenges due to this. We're talking about balancing measurement accuracy with providing a stylish form factor. For instance, how the wearable looks like on someone's wrist, and are we talking something like an Apple type of scenario, or are we talking about something that is maybe something by ASUS or by another vendor? Prototyping these type of devices is costly. It's time consuming. And you have to do it for a great deal of different types of people in terms of what we're talking about here. How stylish is it? Who's going to wear it? When are they going to wear it? Are they going to wear it in direct sun? Are they going to be running a marathon with it? All of these things become a huge challenge for the engineer to design these things. So we need a better way to be more efficient in our designing, and we need a better method of accurately simulating how light goes through these devices, gets absorbed by human tissue, and finally the oxygen content gets out in some form that we can use it accurately to display to the user. So now that I've talked about the two different methods, transmissive and reflective, let's talk a little bit about those two methods. In the transmission method, pretty much what happens is you have an LED source on one side of most likely the finger, and on the other side you have a photodiode or a photodetector that's going to measure the throughput through that particular finger or through some type of tissue. What happens here is we use two different types of LEDs, one in the red visible and one in the infrared. And this light gets passed through the tissue, and at the end we measure it with the photodiode in terms of the signal. In reflectance, it's a little bit different. The LEDs and the photodiode are on the same surface, and light passes through the tissue pretty much in a banana-shaped trajectory that goes into the tissue and then comes out so that you can get the oxygen content and the absorption as the light goes through there, and then gets measured by the photodiode. In the case where you're using a wearable in the reflectance method, the surface may be concave, making the angle between the optical elements variable. And this has to be taken into consideration as well. So let's look at the basics of pulse oximetry. So what we want to look at is both oxygenated and deoxygenated blood at different light which has different light absorption characteristics when illuminated with red and infrared wavelengths. Doing the ratio of the light transmitted through the measurement tissue, we can see at the photodetector a difference between these two types of blood. In the red and IR of oxygenated versus deoxygenated blood for the red and infrared wavelengths, there's an estimate of the oxygen saturation of the blood. And we could take this as a ratio, which is the SpO2 ratio, which is when we compare the two states and we look them up on a table, we see a calibration curve. And this is derived from doing tests on a lot of healthy subjects. In general, a red to IR ratio of 0.5 approximates to 100% SpO2 ratio. A 2.0 ratio would equate to a 0% SpO2 level. So what's the difference here? Well, first of all, we have to figure out what wavelengths are best for taking this ratio. And through a lot of testing, it's been found that 660 nanometers or 0.66 microns and 0.94 microns in the infrared are the most widely used because they work the best. There are more wavelengths that can be used, and in fact, they are used to create some stability in these plot points. But in terms of a formula, if we take a look at that, this ratio is the power on the photodiode in red wavelength divided by the power out of the red LED, divided by the power on the photodiode in the IR wavelength, divided by the power out of the IR LED. So if you look at that ratio, that pretty much gives us a good idea what the SpO2 is when we're measuring and using two LEDs in the transmission method. So if we take a look at the characteristics of oxygenated hemoglobin and deoxygenated hemoglobin. We can see this plot right here. We can see that the deoxygenated hemoglobin, which is HB in a 660, is higher in terms of extinction coefficient than the oxygenated hemoglobin. And it switches out in the IR. So here's your basic idea of how that actually works. And you can take this graph and have a good idea, a snapshot of what's going on here with both types of blood. So the basics of pulse oximetry, when we start going into it, there are lots of factors that go into the SpO2 ratio. Skin, tissue, venous blood, and arterial blood are all things we have to contend with. Each heartbeat contracts the heart and pushes out a surge of oxygenated blood to the arteries. This increases arterial blood volume through the veins and into the tissue. Thus, more light is absorbed during the surge. If light signals received at the photodiode are looked at as a waveform, there are peaks with each heartbeat and troughs between each heartbeat. If the light absorption at the trough, which should include all the constant absorbers, is subtracted from the light absorption at the peak, then in theory, the resultants are the absorption characteristics due to added volume of blood only, which is arterial. Since peaks occur with each heartbeat or pulse, the term pulse oximetry was coined. This understanding solved many of the problems that they had 40 years ago, and they're still valid today. So, there's a lot of challenges. Medical design engineers and scientists developing pulse oximetry devices have unique design challenges, balancing measurement accuracy with stylish form factors, prototyping devices in a timely and costly manner, and finally, we look at device engineers requiring a more efficient way of accurately simulating intensity of light being absorbed by the human tissue. So pretty much the precise measurement of O2 saturation and pulse rate requires an understanding of the basics of pulse oximetry, which are absorbance of each wavelength of light in proportion to the concentration of tissue and blood, as well as the proportion to the length of the light path. Additional factor is the reduction of the bias in these measurements in order to improve accuracy, which can vary greatly based upon low levels of saturation, concentration brought on by anemia, or other vascular conditions. The quality of signal-to-noise ratio between the device and the optical elements is also a problem, depending on the distance that light has to travel through tissue and any other obstructions or external light that could come into play. So our biggest challenge is to probably get rid of stray light in the device itself, which leads to false readings. Minimizing stray light in the device should be one of the major objectives of any pulse oximeter design. And we're going to take a look at that as we get farther into this webinar. So first, now that we've got an idea what the basic principles are, let's take a look at what type of biosensors are already on the market today and take a look at possibly the first oxygen wearable, oxygen content capable wearable. And finally, I've created a generic TracePro biosensor that I'd like to introduce. So the first biosensor that's off the shelf is the MAXIM MAX 3010X integrated pulse oximeter and heart rate sensor. And this is an actual CAD model of that particular sensor. And you can see on the right side, we've got 3 LEDs, one in the green, one in the red, and one in the infrared in the middle there. And on the other side, we have the photodiode. In the middle, we have a blocker that makes sure the light can't go directly from the LEDs over to the photodiode. If you look at the LEDs and the emission, we're talking about an 880 micron, 0.88 micron infrared, 0.66 red, and a 0.537 green. Or if we're talking nanometers, we're talking 880, 660, and 537. And this is an extremely small package. This will fit definitely inside of any wrist wearable. We're talking about only 5.6 millimeters by 3.3 millimeters by 1.55 millimeters. So in terms of having this type of structure ready to go, MAXIM has a really nice product ready right off the shelf. Now, I'm not going to incorporate every single one of the biosensors out there, but just look at a couple here. I pulled the MAXIM integrated, and I'd like to introduce you to the OSRAM Biome sensor. This is the SFH7060. And you can see this thing is quite small. Now, there's the actual sensor there right on screen, right from their data sheet. And once again, you've got 3 different LEDs, 3 different wavelengths of LEDs emitting here. You have a 940 infrared, a 655, and there's 3 of these in the middle there, and then a 530 green in terms of nanometers, and a photodiode on the other side. And this is, once again, in a very, very small package, 4.7 millimeters by 2.5 millimeters by 0.9 millimeters, with, once again, light barriers between the different sections to block optical crosstalk. So this sensor is also a good possibility if you're looking at getting something off the shelf. So right now, state of the art, where are we? Well, there is a wearable right now that uses that OSRAM SFH7060 optical biosensor. It's the TomTom Smart. And you can see a picture of that right here. This image is courtesy of DCRainmaker.com, and it's a complete paper on where the development of this is going. Currently, as I understand, they don't have the oxygen heart rate being captured at this point in time with this device. But they're hoping to provide it as a firmware update. And there's a paper on the LifeQ website that talks about this, and I'm including that website information down here at the bottom of this particular slide. And right now, of course, it's doing pulse rate, which a lot of other products do. Garmin does it, for instance. But this one here has the capability, has the OSRAM sensor, and it's ready to go if they can just incorporate it into a firmware upgrade. So here's our closest option right now. So for this webinar, I decided to take a look at what was out there, and I created a generic model. And here you have a generic model, which includes the 3 different LEDs, one in the green, one in the red, and one in the IR. On the other side, we have a photodiode. And, of course, we've got that crosstalk blocker, which hopefully is going up against the skin so I don't get stray light pass between these 2 mechanisms, the source and the detector. So if we start looking into the design problems that are in wearables, there's a lot of things that can come up. There's false signal due to stray light issues. Once again, stray light rears its ugly head, and we need to get rid of these things. And what's the most likely problem here? Well, people are going to be using this for track and fitness, so we're going to be outside running with these things on, and that sun is going to be an external source. There's your biggest problem. There's also going to be problems due to design constraints and positioning problems on the skin or because of the tissue that's involved. And, of course, this thing's going to be moving. We're jumping around. We're running. There are movement artifacts of the wearable due to all of these things, including sweating and suntan lotion and things, lotions that are put on the body and everything else. That's going to cause us some problems. And, of course, we're going to have to overcome that type of problem. And then, of course, it's going to be on the wrist. So we may have inadequate and probably not the best blood flow due to the wearable constraining possibility of having something tight on the wrist. And, of course, it's going to be out and about. We're going to be sweating. We're going to have lotions. You're going to be jumping in the pool with this thing. So there's going to be a degradation of the wearable materials over time because of external sources. And so we've got to make sure that we're going to get good readings as the thing in terms of mean time before usage out there in the industry and on the body being exercised. So we have to look at that type of problem. Finally, we have to start looking at measurement sites, like if we're using fingers. Fingers are excellent because they're very good measurement sites for SpO2 determination. But the wrist area has poor perfusion index, which is the ratio of the pulsatile blood flow to the non-pulsatile or static blood flow in peripheral tissue. So we've got to be cognizant of that. So we're going to have less of an oxygen flow in the wrist versus the fingers, which is where typically pulse oximeters have been used for ages in the hospital for over 40 years. So let's take a look at a first example here of a transmissive finger pulse oximeter. So in here, I'm showing on the left that a typical pulse oximeter on the finger would have light emitting from the red LEDs going through tissue, and there'd be a photodiode on the opposite side of the device. If you look in the top right-hand corner, you see the TracePro model, and you can see the bulk scattering going and occurring as light is emitted from the LED on the bottom, going through the finger and reaching the photodiode at the top. Well, where do we see some problems in these particular devices? Well, this is usually a very conical type shape, or maybe it's a flattened shape, depending on what type you're using here. But what's happening here is that light goes from the bottom and goes up to the top, but unfortunately, it goes out in all directions. So we're seeing the direct path here that actually goes through the finger. And if we have a completely absorbing cone, which is plastic, around that particular finger, all the light's going to be absorbed, and only bulk scattering that goes through the tissue is what we're going to see. But that's not what happens in real life. Nothing is really perfectly 100% absorbing. And if we made a white reflective plastic and made that as our finger pulse oximeter outside, you can see light would then bulk scatter out to that plastic, would then roll around between the finger and that plastic and get to my photodiode. And in this case, I would have a finger pulse oximeter that didn't work at all because the stray light from the outside enclosure of the pulse oximeter would completely swamp the signal from the bulk scatter. So this would cause a false reading. We'd have a problem here, and we'd have to figure this out and fix it. So this is just a way of using TracePro to do ray visualization. We do a virtual simulation, and we see what the problems are incurred in this particular device. So in terms of what we have here, it's pretty simplistic. We're going from an LED, we're going through some type of tissue, and it's coming out on the other side to a photodiode. Now, the only thing really we can do is actually have something that absorbs that stray light, and that's what we've done with this particular issue. In the past slide, you saw where it was a completely absorbing material, and here's what happens if we have a very reflective material. Let's look at the second example. This is the reflective wrist wearable example for a pulse oximeter. And this is where I really want to go into because this is more of state-of-the-art and what people are trying to design right now. So pretty much you've got tissue, there's the wrist, and you have a wearable that fits on the outside of it. Now, this one's free-floating. And by the way, I don't know if someone's going to ever come out with a free-floating wrist wearable because you have the sun as an external source, and that's always going to be a problem because the light's going to bounce in between there of the sun and the wrist wearable, and we're going to look into that shortly. But in terms of what we have here, for instance, the TomTom Spark is got a nice wristband. It fits very, very snugly on the wrist. If I go back to that particular slide, you're going to see where the LED, it actually juts out a little bit, so the skin is in contact at all times with the portion of the OSRAM biosensor. But in this case, we're now talking about a device that has either 2 or 3 wavelength LEDs. It's going to then emit into the tissue, hopefully follow this banana shape as it goes through the tissue, through the oxygenated blood, and then come out on the other side and get measured in terms of its throughput. Well, pretty much what's happening there is this scenario. This is the correct path that we want to see. We want to see the light coming from the LEDs on the right-hand side, go into the tissue, then bulk scatter through that tissue in sort of a banana-shaped trajectory, come back over, and then get back to the photodiode. This is what we want to have happen. This is the only way that we're going to get correct SpO2 ratio. This is the only way we're going to get the answer that we really want. Well, what comes up is that if we look at the photodiode for the green contribution, the red contribution, and the IR contribution, they should all be about the same, but we notice that it increases. Now, one of the things about light going through tissue is that we know as we go from the visible into the infrared that the throughput gets better. So as we see in TracePro from this simulation, we see the contribution from the green LEDs about 0.015 watts for a 1 watt emitter. It's 0.0153 watts for a red emitter, which is shown in the middle irradiance map there. And finally, on the right-hand side is the IR contribution that pumps up to about 0.016. So as we see, TracePro is doing the simulation. It's showing us exactly what's happening in real life. As light goes from green into the infrared, we get more transmission and more power to our detector, our photodiode in this case. Looking at the next slide, we can see where something happens that we don't want to have happen. This is where light goes from the LED, goes across the crosstalk blocker. There's some type of gap between the biosensor in terms of air or epoxy or something else where light can hit the skin, just the start of the skin, the epidermis layer, and then reflect off of it and go right to the photodiode. So what the crosstalk blocker does here is it stops this path from happening. And this is a problematic path. We don't want it occurring. We want the light to enter into the tissue and go around. If it doesn't, this is exactly the scenario you're going to be seeing. This is why it's important to have that crosstalk blocker. So in this case, in that past case, that was one bad stray light. But look at a even worse stray light. This is the problem from external sources. This can be from the sun. This can be from an overhead lamp. You're talking about the sun in general being 100 times brighter than any of the LEDs used in the biosensor. What's going to happen here is light's going to come from the sun. Instead, we've put the photodiode at the top of the wrist because we want to have a very nice, clear area to take the sampling. What's going to happen here is the sun's going to come through. It's going to rattle between the skin and the wearable band and end up at the photodiode. This is going to cause some problems because this can occur just naturally because we have the band not tightened down enough onto the wrist. It could happen due to slippage due to sweating. It can happen because there are holes or there's cracks in the band due to material degradation, due to skin lotions or whatever that we've put onto the skin. And of course, there's a possibility of damage to the band itself, falling, there's a crack in the band, something of that nature, and light just gets in because of it. So here's what's happening. And if we take a look at that scenario and we do a virtual simulation in TracePro, we see that the sun contribution, even though it's rattling between the skin and the wearable band many times, it still reaches, and this is about an inch thick wearable band is what I'm assuming here, is that we're going to get about 0.018 watts from the sun. This stray light contribution is on the same magnitude as the green, red, and the IR LEDs. So this is going to completely throw off our SpO2 calculation, causing the pulse oximeter to report completely invalid results. So having the sun involved is a very, very bad thing. And these stray light issues can be a very poor capability in terms of getting a good reading. So what are the benefits of software simulation? Well, if we've seen from the past slides, it's well known that using simulation for virtual prototyping decreases the trial and error prototyping process. You don't have to make as many iterations. It reduces the amount of money in terms of time and money because you can do a quick scenario in just a few minutes. Software simulation allows users to determine both throughput efficiencies accurately through different materials for different tissue types and looking at non-uniformity issues. It provides a visualization of seeing where the rays are going and seeing crosstalk and stray light issues that can't be seen by normal visual processes. Finally, you get to create better product because you can do more iterations. You have design tools that let you see into the design and eliminate unwanted and problematic features, and provides an optimization capability to create the very best design through multiple iteration techniques. So in conclusion, TracePro's analysis features that we've seen here give the designer the tools to create better product. So I've not shown every single one of the capabilities of TracePro. For instance, I didn't show a Flex report. The Flex report is great. It's like an Excel spreadsheet that shows the absorption and throughput to any surface in the model. So you can see where your light's going, where you're losing it, and if you figure out where you're losing it, how to combine that back into the equation to use it if you're lacking enough power. And so instead of having to put another LED or brighter LEDs, you might just be able to use the Flex report to figure out where light's going and then to reuse it. There's also a 3D irradiance and luminance map. This allows you to grab any object or part in your model and show the amount of power on that particular part. And you do it visually. It shows like a power flow. You can do it in a pseudo-color plot or a grayscale plot and see just how much power is going through. And you're seeing in a lot of cases how light is mapping the flow of anything from the LEDs that are emitting from maybe the external sun or some stray light issue that you're having in the particular pulse oximeter. Finally, you get to see rays tracing from the LEDs through the system to the photodiode. And that gives you a lot of information where you're losing power. You're seeing if you're actually getting the bulk scattering that you expect. You get to hopefully see that banana trajectory that you expect to see there. And finally, if you have external stray light sources or stray light inside the mechanism, you can see that occurring with this visualized ray tracing. Finally, you can use advanced path sorting to analyze and minimize crosstalk paths in the light guide. And you can look at each one separately and see that contribution. So this is the type of features that TracePro gives you to quickly virtual prototype and get better answers. I have a whole bunch of references that I used during this talk, And if you're new to pulse oximetry, I would suggest that you download the Principles of Pulse Oximetry from the oximetry.org site. That's my reference number 1. The nice little chart the graph that I showed showing the oxygenated versus deoxygenated hemoglobin, that's reference number 2. If you're interested in some of these off-the-shelf sensors, please use references 3 and 4 to look at the MAXIM MAX3010X biosensor and the OSRAM SFH7D60. Finally, if you're interested in the TomTom Spark and maybe some of the information about LifeQ, take a look at DC Rainmaker. They've got a very good, nice article about that. And finally, if you're interested in like the Philips off sensors and their capabilities, go over to Philips Medical Systems and see them. Finally, I'm going to turn it back to John Wallace here, and we'll get into the question and answer section.
Okay, thank you, Michael. We're now in the Q&A portion of the webcast. So to ask a question via the web, type your question into the Q&A app that you find at the bottom of the screen. I would like to mention that if you ask your question too late or if your question isn't answered in the live webcast, all questions will go to Michael later and he can answer them at his leisure. So let's move to the first question. How does your RayViz product help do virtual simulation of pulse oximeters?
I'm glad that was answered. Pretty much RayViz allows you to do ray visualization. So all the things that you just saw in terms of being able to see where light's going in the sensor and through a particular object can be done using the RayViz product. It just shows you rays being traced through it. Now, one of the things is, right now we're not doing the bulk scatter, but we should be able to do that in the future with the product as we come along. But right now we're just doing like the stray light issues and things of that nature where we're seeing crosstalk and properties. So in terms of the bulk scatter, we haven't got it there yet, but in terms of all the other things that I've been showing, RayViz does have that capability. And since the SolidWorks add-in, all you do is add your optical properties to the system tree. You then quickly trace the rays, and then you can see the visualization of those rays directly in your SolidWorks system view.
Okay. Next question. Are there more off-the-shelf biosensors out there besides MAXIMs and OSRAM?
Yeah, there's one out there from Philips. I believe Massimo has one. Doing a web search should probably help you out there, but yes, there are more out there. And I'm probably sure there's more coming every day because as we see, if people start getting into the wearables and wanting the heart rate monitoring with oxygenation, it's going to be huge. I would like to have one as a matter of fact because you just want to know how you're doing in terms of when you should stop. If you're out of breath, you want to have confirmation of that, and that's pretty much going to be a huge market in the future.
Mm-hmm. Okay, a couple of questions here that I would ask too. Does TracePro have a human tissue catalog?
Yes, we have a human tissue catalog. It's based on Valery Tuchin's work. He's one of the best known people out there in the industry for taking samples and going through and creating. We use the Henny-Greenstein function, and he supplies a complete definition of human tissue and for the different layers inside of the skin. And we've been using him and following his capabilities and his papers for the last 10 years. And a lot of that information is in our human tissue catalog.
And another similar question, I'm going to skip around in this list of questions here, but does the TracePro have a realistic built-in skin model?
We do have a example that you can download that has everything preset in terms of thicknesses and everything else that you can go through as an example, but it also has a full catalog of different types of skin tissue in terms of epidermis, dermis layers, and things of that nature. And you can create your own. It's very, very simple to custom create your own catalog by just entering the anisotropy and the scattering coefficient of the particular tissue and then saving it with a name to be used for later on.
Okay. What other type of stray light issues are possible in a wrist wearable?
Well, anything that can happen in real life in terms of if you've put in, you can have things like, start putting in the PCB board itself. It can be a propagation type mechanism for sending light in spurious locations around the sensor. You could be bouncing off the top, for instance, of the sensor and then come back to the PCB and then drop over to the photodiode part. You can look into that type of problem. So the internal mechanisms of the biosensor itself can become stray light issues, for instance. That's just one of the ways. It more depends on the particular system you have, but when you put the whole model of what you're trying to put in together as a pulse oximeter, the whole thing can be modeled, and you can never understand every single possibility. But that's where the ray visualization comes into effect, where you can turn everything on and then see what gets to the photodiode, and then go backwards and see where that light's coming from using TracePro, and then find those stray light sources.
Mm-hmm. Is there a way to optimize angles or dimensions, the incremental variation of one or more parameters automatically or semi-automatically?
Yes, we have an interactive optimizer inside of TracePro, and we have the capability to specify anything that you model in terms of CAD geometry in the optimizer. You can specify it as a variable and how far you want that variable to move around, and then see the results and have the program use a nice little local optimizer, the downhill simplex method, to go through and then optimize based on that variable and the mirror function that you program into the program, in the optimizer, I should say.
Mm-hmm. What is the solver for the ray trace?
We use Monte Carlo ray tracing.
Okay. I think we have time for 2 more questions.
Okay.
As I mentioned, 2 or 3. As I mentioned, any questions that aren't answered live can be answered later by Michael. Can the software help in the determination of the minimum LED flux requirements for pulse oximetry?
Definitely. So you're creating an actual model of your system. You can then specify the bulk scatter inside of the tissue and then find at the photodiode the exact amount of power that comes over. Of course, every single biosensor, if you look at the data sheet, will tell you what the minimum LED flux requirement is. So when you set up the whole system inside of TracePro, you will then have that number as a radiance map flux, and you'll know if you've met the requirement or not.
Okay, using a laser irradiance source in a darkroom arrangement, would you still suggest a crosstalk blocker, considering this to be a question regarding experimental setup based on simulation outputs?
Well, it depends on the setup of where your LEDs are positioned to your photodiode or your detector. If there's no way for the light to go from one to the other because you're in a dark room, then no, you don't need a crosstalk blocker. But if there's any possibility of a straight shot where the light goes from the LEDs over to the photodiode, or if it can just reflect off, if you have tissue where it's going to reflect off the very skin and just go directly to your photodiode, that's going to be a problem. You're going to need something to block that path because you want light to enter into the skin. You don't want it to just reflect off of it because you want to get that oxygen content. So the only way to do that is to stop that second, I believe it's slide. Oh, let me see. I think it's slide 20. Slide 24 shows this. And so if you have to get rid of that particular contribution, you're going to need the crosstalk blocker.
Okay, and the last question.
Sure.
Can you summarize the simulation process to get scatter graphs? I assume 3D input, optical characteristics of detector and emitter, some sort of model for the scattering of light inside the flesh is a function of O2 content.
Right, so you're going to specify using the Henry Greenstein function, a phase function that specifies how light scatters through the flesh in terms of O2 content. You're going to specify the LED, and you're going to specify both its spatial and its angular and its wavelength information. You're going to specify the detector and how well it absorbs light as well. And of course, you're going to have a full 3D CAD geometry, and you're going to be able to specify how each one of those surfaces reflects, transmits, and scatters and absorbs light. So yes, everything will be available inside the program, and you will get irradiance plots that show you how the power goes through every single one of those pieces of the puzzle, which is every single surface in that model. And you can see all of it as at your leisure to go through and see how the light propagates.
Interesting. I've always wondered personally when Apple would be getting into this market with some of these devices, but I don't know if you know anything about that.
Apple is working on. I do know Apple is working on this capability and bringing it into the iWatch. Currently, in the systems I've seen, they don't have a biosensor in that unit, but that doesn't mean they're not working on it, and that would be up to them to comment on, because I'm sure Apple is very, very hush-hush about any type of work that they're doing, but I wouldn't see why they wouldn't want it in their watch.
Yeah.
I mean, they usually are state-of-the-art, and they usually come out with these things, before anyone else does. So it would be very surprising if they weren't working on it to me.
Interesting. Okay, thank you, Michael. Would you like to make any closing remarks?
Yeah, I did have one thing to say. This happens to be the OSRAM Biome, and inside here, I just want to let everyone know that this is not just a simple system. There's actually 5 LEDs in here. There are actually a set of 3x green. I'm sorry, I said there were 3x red. There's actually 3x green. That's a thing I wanted to clear up there, just so everyone knows. That's about it. And if you have any questions or anything else, don't hesitate to email me. I'll be glad to talk to you about this. I'm always interested in finding out more about this particular device and what people are doing with it.
Great. Well, on behalf of Laser Focus World and Penwell Corporation, I would like to thank Michael Goblin of Lambda Research Corporation for today's presentation, Virtual Simulation for Pulse Oximetry Wearables. This presentation will be available within 24 hours and can be accessed from the homepage at www.laserfocusworld.com. And by the way, the PDF of this presentation is available now at the bottom of the screen. A reminder, email message for the archive will be sent to registrants complete with a link to the archive. We thank you for joining us today and look forward to future webcasts.